Okay, and as noted before, you know that a reaction is spontaneous if the cell potential is greater than 0. So that's a very useful fact, and it will come into play with some of the examples we do here. So in example 1, the standard cell potential of a silver copper galvanic cell has a value of 0.46. The cell reaction is given with reference to the standard reduction potential of the copper electrode to determine the reduction potential of silver ions. Okay. And it also asks us to use proper cell notation to represent the cell. So in this case, the copper is actually being oxidized, so it's the anode. So you've got copper in a copper solution connected by a salt bridge to a silver solution with a silver electrode. So that's the proper cell notation. We know that E cell is the reduction potential at the cathode minus the reduction potential at the anode. In this case, it tells us that the cell potential is 0.46, and we know that the cathode is silver. So that's our unknown, and we know from our previous example that the anode has a cell potential of 0.34. So this shows us that the cell potential of silver is 0.80 volts. And if you look at the standard reduction potentials, you'll see that that is the case. Number 2, it asks us to predict the reaction that will occur when nickel and iron are added to the solution that contains both nickel and iron ions. So what we have here is two potential reduction reactions. So the nickel ions could be reduced or the iron ions could be reduced. And what we want to do is look at the reduction potentials of each of these reactions. For the iron, it's negative 0.44 volts, and for the nickel, it's negative 0.25 volts. And the one that is higher up on the reduction potential list, or has a higher reduction potential, which is the nickel, is going to be reduced. And the other one is going to be oxidized. Okay, so what we have here is the nickel is going to react in this same way. The iron, the reverse reaction is going to happen. So the iron is going to be oxidized. So to write the reaction that's going to occur, we're flipping the first reaction and adding it to the second reaction. And in this case, I don't need to do anything with the electrons. They're already balanced. In question 3, it asks us to use the positions of the half reactions to predict the spontaneous reaction when Br minus, SO4 2 minus, SO2, and Br2 are mixed in acidic solution. So this one is a little bit less straightforward. What you need to do is look at the reduction potentials and find the appropriate reactions that apply to these conditions that are given. So there's one reaction that is SO4 2 minus plus 4H plus 2 electrons going to SO2 plus 2H2O. Okay, and the reduction potential of that reaction is 0.20. The other reaction is of bromine gaining 2 electrons to form Br minus, and the cell potential of that is 1.07. Okay, so I really encourage you to look carefully at the reduction potentials and see how I made the decision to choose those particular reactions. Now, in this case, the bromine is the one with the higher reduction potential, so it's the one that's going to be reduced, and the other one will undergo an oxidation reaction. So much like I did before, I need to reverse the reaction that is actually undergoing oxidation and add it to the reaction that is undergoing reduction. Okay, and so this is the overall reaction that would happen spontaneously in that system. Okay. In example 4, it asks what the cell reaction would be and the standard cell potential of a galvanic cell employing the following reactions. Okay, so again, we're comparing two reactions. The one with the higher cell potential is the one that's going to be reduced. Okay, the one that is with the lower cell potential is the one that's going to be oxidized. So this one is the cathode, okay, and this one is the anode. Okay, so if we want to find the cell potential, I'm going to take the cathode of 0.34 and I'm going to subtract the anode reduction potential of negative 1.66. And I have a cell potential of 2 volts. Now, in order to actually write the overall reaction, I need to be mindful here. I know that the first reaction needs to be flipped because it's the one that's being oxidized, but you can also see that in this case, the electrons that are transferred are not the same, so we need to take that into account as well. And notice that this has nothing to do with the cell potential, so I'm not concerned about multiplying these reactions when I calculate the E cell, but I am concerned when I write out the balanced reaction. So when you multiply them and then recombine them, okay, you're left with 3 copper plus 2 aluminum goes to 2 aluminum plus 3 copper. And as is the same as before, if we look at this reaction, both the atoms and the charges are balanced in this overall reaction. Okay. In this next example, very similar to the previous one, the one with the higher cell potential is going to be the one that's reduced. The one with the lower cell potential is going to be oxidized. So in this case, the overall reaction is nickel oxide plus water goes to nickel hydroxide plus iron hydroxide. In this case, I didn't need to multiply because the electrons are the same in both reactions, but when I flipped the first reaction, the hydroxides ended up canceling each other out. So I really encourage you to take the time to set it up and make sure that you know how to recombine the reactions and get the appropriate overall cell reaction. Okay, the E cell, by taking the cathode and subtracting the anode, we are left with a cell potential of 1.37. In number 6, we're asked to determine whether the following reactions are spontaneous as written and give a reaction that is spontaneous if needed. So what we have to do here is look at which one is the anode and which one is the cathode, not based on their position on the activity series, but the way that it's written. So in this case, the copper is losing electrons, so the copper is actually the anode. So when you find the cell potential, we're going to take the hydrogen electrode, which is 0, and we're going to subtract the copper reduction potential, which is 0.34. And so in this case, we have a cell potential of negative 0.34. Okay, it's less than 0. So the reaction is not spontaneous. Okay, if you want to write the spontaneous reaction, you write the reverse reaction. So the reaction of copper plus hydrogen going to Cu plus 2H plus is the one that's spontaneous. If the forward reaction is not spontaneous, the reverse is, okay, and that makes sense based on the fact that we're going to switch these around. So the copper would be the cathode minus the anode, and it would simply be positive. Okay, same magnitude, different sign. So in this next one, identifying the actual half reactions is the challenge, but you can see that if you look carefully, that copper in this case is the anode, and the reaction with nitrate and the acid to NO and H2O is the cathode. Okay, and in this case, the E cell is the cathode or the nitrate reaction of 0.96, minus 0.34, which is our copper reduction potential, and we get a voltage of 0.62. Okay, so therefore this particular reaction is spontaneous. And that concludes this lesson.